Welcome, everyone. Thank you so much for joining us today for our very last Grasp on Robotics series. Just a quick reminder, this and previously recorded talks can be found in our YouTube channel and website. Also, throughout the talk, please submit your questions using the button at the bottom of your screen. These will be answered during the Q&A panel at the end of the talk. Now, I would like to introduce our Grasp faculty host for today's talk, Dr. Michael Posa, Assistant Professor of the Mechanical Engineering and Applied Mathematics Department within the School of Engineering here at the University of Pennsylvania. Thank you so much and have a wonderful talk.
Thank you, Gabby. It's always a pleasure to have with us a GRASP alumni, and I'm very pleased to be able to introduce Aaron today. So as many of you know, Aaron Johnson did his PhD here at Penn in the COD lab. You know, as I was starting my PhD and getting along there, some of Aaron's work, sort of the beautiful blend of experimental results along with the mathematical rigor was something that really spoke to me. So I've sort of known Aaron's work since, you know, very early on in my academic career and have followed it very closely, as I'm sure many here have as well. Aaron did his, I believe, undergrad at Carnegie Mellon before his PhD here, returned to Carnegie Mellon for a postdoc, working on some manipulation work and convergent planning, and has since then started the Robomechanics lab there at Carnegie Mellon in the mechanical engineering department. He's won an NSF Career Award, a Young Investigator Award from the Army, and has done some really fantastic work that I'm excited to hear him talk about. So Aaron, welcome back virtually. And thank you for taking the time out of your busy day and sleepless nights.
Thank you, Michael. Good to be back in Philadelphia. Well, not quite, but virtually at least. Good to see many familiar, not faces, but names on a list over on the right. So that's good. Let me share my screen here. All right, hopefully that's coming through. So today I want to give some updates on tools that we've been developing in my lab for handling contact and handling these kinds of discontinuous systems. And overall, what am I interested in? I want to make robots that can work out in the real world. And we're very interested in my lab in applications like planetary exploration, environmental monitoring, looking for contaminants in soils and that kind of stuff, as well as working in human spaces, so home assistance in cluttered indoor environments and urban mobility. And what's the problem with getting robots to work in the real world instead of in a controlled environment like a factory, is that the world is a mess. And whether we're talking about natural terrain or man-made terrain, even things we think of as very smooth and regular, like staircases, are often just as messy as the outside world. So here, this is what staircases look like in Pittsburgh, and it's very challenging to move around in these environments. So let's look at some of the specific challenges that come up. So here, this is a video from my PhD when we took Rex out to the desert, and this is sort of the blooper reel of the robot. Mostly did pretty well on this rocky hill, but here's a bunch of times that it didn't work too well. And all of these times that it sort of rolls over or flips or runs into something, almost all of them really come down to either an unexpected contact between the robot and a rock, or a missed contact where it tried to put its foot down and there wasn't a rock there and it rolled over. And that's sort of the common theme running through all of these, is that it either just ran, nose into something, or that it smacked its foot down and that foot knocked it over in a way it wasn't expecting. And this sort of uncertain contact conditions is not just a problem for robots. It's also a big problem for humans. So here, this is a great YouTube video of a New York City subway staircase that over the years has settled ever so slightly. And just looking at it, you can't kind of tell, but there's one step that's a fraction of an inch taller than all of the other steps. And you can see as people are going along, almost everyone seems to trip on that same exact stair where they're trying to swing their foot up to the next step, and it just clips the corner a little bit, and it causes major challenge. All right, so these kinds of unexpected contacts are a big problem for anything that's trying to move through the world. And so this, if I sort of boil down, what are the key challenges that a lot of the projects in my lab are thinking about? They really come down to contact and uncertainty. And so contact, the issue with contact is that it introduces discontinuities in the dynamics. And so if your foot is just above the ground, you don't get any contact force. And then if you're touching the ground, you can have a large contact force, and those can be very close together. And then uncertainty, when we can't control the environment, if we're not going to polish our factory floor down to be perfectly smooth, then we need to be able to handle a fair amount of uncertainty in our state, in our dynamics, and in particular then in our contact conditions. So for today's talk, I'm going to focus mostly on contact and talk about two different tools for how we can handle contact using controls techniques. So to launch into this, I wanted to give just a quick background on contact and how people have modeled it and handled it in different mathematical models in the past. And in particular, thinking about simulation. So if you wanted to build a simulator for a robot that had changing contact conditions, there's sort of three different strategies that people typically use. And the first is called penalized or soft contact, where you basically swap out the ground for a series of spring dampers, and that allows you to sort of squish into the ground and come back up. And this is very easy to set up in a generic way and simulate more complicated systems. But it means that you do end up with your foot sinking below the ground, and it can be very hard to tune these spring damper type terms so that you don't accidentally push too hard and end up flying off to the moon when you go a little bit too far into the ground. The second approach for simulation is an event-driven or a hybrid systems scheme where you use continuous integration tools until you reach an event, in this case, a contact event. And then you stop, you back up, you figure out exactly when it happened, and you apply a discrete impulse, and then you can restart the simulation after that event. And so this is nice. It's sort of exactly, I think of this is how physics was explained to you in high school, right? And that you're moving along, and then you hit something, and there's an impulse, and then it continues on. And the problem is that you have to stop, right? And then so every time you have an event, every time you have a change in contact condition, you have to stop your integration and do something, and this can really slow it down if there's lots of contacts. And then the third approach is called time stepping. So the idea here is that we're going to have discrete time steps, and every iteration we're going to move forward by that amount. So whatever the dt is, we'll always move forward that amount, no matter how many contact events happened in between. And so we're just going to move forward however many, 1 millisecond, 10 milliseconds, whatever it is. Maybe there's a contact, maybe there isn't. Maybe there's 10 contacts, maybe there's hundreds of contacts in that dt. We're just going to try and come up with a consistent solution at the end of that time step so that then we can keep moving forward. And here there's a quote. So this time stepping scheme is order 1, meaning that it's a constant, or it's a linear approximation, and is not very accurate unless h is decreased a lot. So if that time step is really small, it's going to be accurate. But if it's larger, then it's going to be a pretty inaccurate way to integrate your dynamics. And so it's preferred for systems with lots of events only. And so most of the work that I do is in this middle category of hybrid system or event-driven. And just to give you some examples, here's a bunch of robots that I would just say are good candidates for this kind of hybrid system, event-driven way of thinking. Where as you're watching these videos, maybe you have to slow them down a little bit, but you can say, you can see each contact change. This foot touched down, and this one lifted up, right? And there's not so many contacts that we would have to stop so many times to handle it. In contrast, here's a bunch of robots where this would not be a good way of simulating the robot. So in the upper left, we've got a robot going through underbrush where it's bumping into lots of different vines and leaves. This video, by the way, is taken by someone you guys may know Justin Yim. Justin, not Mark, Justin Yim. But these other ones, we've got this rolling contact with the snake robot. We've got sand. We don't want to think about every time the foot hits a different grain of sand. That's not, we don't want to stop our integration and have to handle that, or every time two sand particles bump into each other. So for these systems, if your robot looks like one of these, then don't take the sort of hybrid system approach to modeling. All right, so that was some background on simulation. The first sort of tool that I want to talk about is has to do with trajectory optimization. And so just some background on trajectory optimization. What we want in this section is to find some path, some trajectory that satisfies different constraints, and also maybe minimizes something like minimum time. So if we want to go from the yellow circle to the green circle, we'd rather take the path on the right, which is nice and short, than the path on the left. And the key challenge in trajectory optimization is that we have to discretize the trajectory somehow. We have to come up with some finite number of decision variables so that we can then use an optimization solver to represent that trajectory and try and find an optimal trajectory. And so that can be either storing our control input at every step along the way. That can be using different curves to represent the trajectory. At the end of the day, we need some finite number of decision variables that we can then optimize over. And why am I talking about trajectory optimization? What in particular for my lab, what do we want out of it? And there's a few things that we would want to get out of a trajectory optimization. And the first is sometimes we really want to know what's the fastest way to get from A to B, right? And so if we want to learn a new controller or the most efficient controller that we can then have our robot perform better. But trajectory optimization is actually a tool that can help us answer many more questions than that. And in particular, we like to use trajectory optimization to try and answer questions about morphology. So the question is, if here in this on the left, this sort of biped with wheels, we were asking, what is the best you can do with the robot that has wheels instead of feet? What's the best the robot with the feet can do? What's the best the robot with the wheels can do? And now we can really tease out some questions about what the best design is. And ultimately, we'd like to be able to run these kinds of trajectory optimizations online as we're running, instead of a sort of offline planning phase, in order to get the robot to react as it's running on different terrain. All right, so let's look at some more details. So if we wanted to come up with a trajectory, to optimize the trajectory that included contacts. So let's say we're this point particle, and we're going to throw it, and we hit this one contact, which I'll call the ground. And then it slides up that other contact, which we call the hill. One way that we can sort of represent this trajectory in a trajectory optimization framework is to decide ahead of time the order in which contacts will happen. So we'll say, for a while, we're in this blue region where we're in the air, and then we're in this green region, we're on the ground, and then we're in the red region, where we're touching the hill, right? And I just, for some reason, I know what that sequence is. All right, then what we can do is, if we can break up the trajectory that we're trying to optimize, label ahead of time different phases of it. In each phase, we'll apply the dynamics with the correct contact forces. In between the phases, we can insert impact laws that say how we transition from being in the air to being on the ground. And then at this point, it actually looks just like a trajectory optimization problem that doesn't have any contacts in it, actually. And so we call this hybrid trajectory optimization. I don't think the terminology is super consistent between authors, but this is sort of, we've set up a hybrid system. This is the order in which we're going to make these transitions, and we plug it in. And we can get here's some example outputs from a hybrid trajectory optimization, where we've said the feet lift off at the same time, or that they touch down. I think it's usually the front one before the back one. Right, and this is nice. What are we trying to do here? So this was trying to look at jumping, accelerating, and decelerating, both with and without a tail. And so this is sort of in that category of trying to understand design and saying, what's the fastest you can jump? What's the fastest you can stop? with the tail and without a tail. And in particular, in this study, we were looking, this is sort of a sidebar, but we were looking at aerodynamics and how do aerodynamics affect your ability to start or stop or jump or do these other sort of agile behaviors. And so as a little preview here, I won't spend too much time talking about it, but we then took those trajectories from that hybrid trajectory optimization, and here we're running it on a robot that has an aerodynamic tail, and looking at how fast it can jump and start and stop and do these kinds of behaviors. All right, so in this case, the behavior is pretty simple. We're jumping. So maybe there's a little bit of decision to decide, does the front leg lift off before the back leg or vice versa? But there's not a lot of choices in terms of what the contact sequence was. And so that made this a good candidate for this kind of hybrid trajectory optimization. But what if we can't specify the contact sequence ahead of time? Lots of systems, there's going to be more choices, and we don't necessarily know what we want to hit when. And so an approach developed in part by Michael Posa, who you just heard from, is called contact-implicit optimization. It goes by several names. That's the one I like. And the idea is that at every point on the trajectory, we're actually going to allow contact forces from any contact, right? Which seems nuts, right? Every single contact can simultaneously apply force on every single point on the trajectory. All right. So we got to dial it back, right? We can't have that at the end. And so in addition to sort of allowing those forces, we then add these constraints at every time. And in particular, the complementarity constraint that says at the optimal solution, the contact force and the contact distance need to multiply to 0, meaning either the force is 0 and your position can be whatever it is, or the distance is 0 and then your force can be whatever it needs to be. All right, so we sort of allow everything to have any contact force, and then we constrain away to make sure that at the end, the solution is consistent. And the other thing to note with this contact-implicit scheme is that it's that the forces and impulses are then combined, similar to that time-stepping simulation scheme, where this is sort of the net effect from forces and impulses from that contact over that full time step. But we're not going to resolve whether it was a force or an impulse or anything that happens in between these time steps. All right, so this is sort of the background on trajectory optimization with contact. And in this first part, I want to introduce our recent work on how to use higher order orthogonal collocation to get more accurate trajectory optimization. So what does that mean? So in this contact implicit optimization scheme, really what we're doing is you're using implicit Euler integration, meaning first order, which is not particularly accurate. And so this means that our dynamics are not faithfully followed in between the DTs, in between the samples that we've taken. And in particular, you can think of it as a zero order hold. You could think of it as a line in between. We don't really know what the trajectory is in between these states, right? And so we'd like to have a more accurate way of representing our dynamics. And so if we didn't have any contacts, we would use, rather than a straight line, we would use a higher order curve. But the problem is that if we're trying to fit a smooth curve to a trajectory that has a discontinuity in its velocity, it's going to be really hard to fit that smooth curve to this kinked trajectory, right? And so whether it's here, I'm showing collocation, Rideau collocation polynomials. You could do Bezier curves, however you wanted to represent the curve. If you're trying to fit a smooth curve to a kinked trajectory, it's not going to work very well, right? And so there was even a quote here: if no collision detection is performed, the integration method cannot exceed order 1, exactly because of this problem, right? We can't fit a smooth curve onto a kinked trajectory. And the problem with this logic is that's true for time-stepping simulation, right? So time-stepping simulation is stuck at first order integration, but it's not true, it turns out, for optimization. So in an optimization scheme, we can simultaneously solve for when those contact events happen and for the trajectory in between them. And this means that we can kind of line up the boundaries between our different piecewise polynomial trajectory so that on each phase, we have a nice smooth curve, meaning that we can integrate it with higher accuracy. And then at the boundary, we can capture any discontinuities. So the idea is that we're going to we're going to use higher order curves. We're going to then enforce that any impact event happens right at the boundary so that we can kind of capture those discontinuities while still having smooth curves everywhere else. All right? And then the same optimization that's figuring out where we're going to go also figures out when those contact events happen so that we can line up the impulses. All right? And so, so our solution, again, what we're going to do is we can now, instead of going from this sort of straight line trajectory here, hopefully my cursor is showing up in Zoom here, right? So this sort of first order version, we have had straight lines between everything. We're going to replace that with this hybrid higher order trajectory optimization, where we can now have these higher order curves that we can integrate more accurately. And at the boundary, we're going to allow impulses. So we can add in explicit impulses. We can now tell the difference between a contact force and an impulse. And we can have discontinuities in our velocity. We have these kinked trajectories that are more faithfully follow our dynamics. All right, and then the rest of it kind of looks pretty similar to regular contact-implicit trajectory optimization. So we still need to have a complementarity constraint. We still allow contacts to change at any time, add and remove however we need. All right, and really by switching from a first order polynomial to a higher order polynomial here, what we've essentially done is we've taken the contact-implicit trajectory optimization framework and swapped out the time-stepping integration for an event-driven simulation. All right, and so all of the benefits and costs that come with that will come along with it. All right, so that was a lot of sort of arrows and curves. What does this actually look like? So here's some experimental results with this higher order trajectory optimization. So first experimental question was, did we actually achieve this sort of higher accuracy that we were going for with these higher order curves? And so for this first example, we're using a simple system so we can run many, many trials. So this is a swing up pendulum with a hard stop, so it can have plastic impact with that hard stop. I know this is kind of an eye test here, but what we can show is that here I'm showing on the x-axis is the solve time, the y-axis is the error, the integration error. So you want to be towards the lower left. And this pink is sort of the implicit Euler, the first order methods. And then down here in the blue is the higher order collocation. So the smooth curves with our method. And we can see that we can get sort of faster and or more accurate solutions to the trajectory optimization problem. All right, so that was a very simple system. How can we scale this up to a much larger problem? So in the second example, we have a biped walking. So each foot has heel and toes. There's 4 possible contact points that can be in any combination. And we've set it up with 300 finite elements. There's like 90,000 decision variables, 100,000 constraints. This takes about 3 hours to solve. Very large problem. But we are able to get solutions to this sort of humanoid running across the 10-meter run with a little gap in the middle that it has to jump over. So if we look at the solution to a contact-implicit, I think we asked for minimum time, so get over there as quickly as you can. You can kind of see the legs are flailing around all over the place. And this is really the trajectory optimization taking advantage of the fact that it doesn't have to stay that true to the dynamics. Right, that because it's only first order integration, it can take kind of pretty big steps, and the dynamics don't quite look realistic. With our higher order trajectory optimization on the bottom here, we get a much smoother trajectory. We get a much more accurate representation of our dynamics. So you can sort of look at these pictures and decide which one looks more realistic, or you can look at the numbers. With the first order, we get about 10 to the negative 2. So this is like a centimeter scale error in our dynamics. And on the bottom, we get 10 to the negative 4, which would be like 0.1 millimeter level of error in our dynamics. All right, so we're able to get much more accurate trajectory optimizations out. And so the key takeaways from this first problem is that we can actually have higher order accuracy with our contact-implicit problems. All right, and the key is to really limit the contact changes to the boundary between these finite elements, so we can kind of capture those discontinuities in isolated places. And then we can use however high order, whatever smooth functions we want in between. And this results in either more accurate and or faster solutions. They're still not particularly fast. This is still a very hard problem for numerical optimization. So that, again, that humanoid problem that took about 3 hours to solve for something that's like a 10-second trajectory. And so we're a little bit faster. We need to get much faster. I think the key is going to be better NLP solvers, better optimization solvers, better numerical methods. And so for that, I would refer you to my colleague Zach Manchester, who's looking at better solvers for these kinds of problems. And then one future direction that we're taking this work is thinking about, this was generating a trajectory that is optimal, but is not particularly robust, potentially. We have some other work. Remember I said there were sort of two challenges for contact and uncertainty. We have other work doing trajectory optimization to try and minimize uncertainty. And we're working now to try and combine these two together. All right, let me take a breath here for just a moment because I can't see the Zoom window. Well, all right. I assume someone will tell me if I cut out or if Zoom's doing something weird. Okay, so that was part one, was trajectory optimization. So how do we plan a trajectory that includes changes in contact conditions? In part two, I'd like to talk about Kalman filtering with contact, meaning how can we do trajectory tracking? How can we do state estimation when we're following a trajectory that has changes in contact conditions? All right, and so just as a primer, if you haven't seen Kalman filtering before, this will be great. If you have, this is mostly to get our terminology all aligned. But the idea with Kalman filtering is that we're going to represent our state as a mean and some probability distribution, typically a Gaussian distribution around our state. And what we want to do is we want to track that over time. And so as we move forward, the first step will be a prediction step. So we're going to move our mean forward following our dynamics. So we have some model of our dynamics. We say, if I was there, this is where I will be. And then we update the uncertainty around that mean as we go. And so as we move forward, until we get any sensor measurements, our uncertainty is going to slowly grow over time. All right, and that comes from this prediction step, and the growth comes from this additive extra noise that we put in there. All right, then the next step in Kalman filtering is to update the update step with a measurement. So if we have some sensor measurement that says, I see something over there that I know, that sensor measurement implies that I must be somewhere in this probability distribution. So you can think of the sensor measurement as giving you its own mean and distribution. So this is sort of the likely position that we are in from that sensor measurement. And that'll disagree with our previous estimate. And so then the magic in Kalman filtering is, how do we then combine our prior estimate and our measurement in an optimal way to get a new mean and distribution? All right, so then we increased, as we were moving forward, our uncertainty was increasing. And then as we take sensor measurements, that should improve our estimate of where we are. So our uncertainty is going to decrease. Okay, so that's the sort of general Kalman filtering picture. What if we have a contact event? So what if I'm going to focus on the prediction step, but it's the same sort of story with the update step. What if there's an impact event? What if our foot hits the ground during that prediction step? So if we look at the equations for our continuous prediction, so if we didn't have an impact, then our uncertainty in particular is propagated using the Jacobian of the flow. So the Jacobian of our dynamics as we're going forward. And that sort of captures if the dynamics naturally grows or shrinks the uncertainty. How does that sort of propagate through? All right. So for the discrete step, so when we're taking these, so when we have a contact event, we need to apply like a plastic impact law or an elastic impact law or some other hybrid transition. We know what to do with the mean, right? Like if we just had a single point, we know how to simulate and model what happens to our mean as we go forward. And that's typically captured in a reset map. So we say that our state after our impact is the reset map applied to our state before that impact map. And that's this function R. And so it might naturally say, well, so our uncertainty should probably get updated using the Jacobian of the reset map instead of the Jacobian of our flow. All right. And so that seems like a pretty natural thing. So that should capture for that reset map, how much does the reset map grow or shrink the uncertainty? All right. So let's see if this works. So here, we tried to come up with the simplest hybrid system we could. And I love staring at this animation. So we could just look at this for a while. We call this the cheese grater animation, although maybe we should turn it on its side and have it sort of, anyway. So this is super simple hybrid system. The dynamics in each mode, there's two modes, dynamics is constant. All right. So as you can see, when it's on the left-hand side, nothing's coming, getting bigger or smaller. Same on the right-hand side. It's just shifting along. Dynamics is 1, -1 on the left. Dynamics is 1, 1 on the right. Very simple. The guard is a line. So the guard set, that's a boundary between our hybrid systems. It's just that dotted line in the middle. It's the x = 0 line. The reset map is identity. So that R that I talked about, the reset map, there's no impact. Nothing changes at the boundary. All right. It's just identity. So you get to the edge and then you continue going. In this animation, I've taken out the process noise. So we're not even slowly expanding our uncertainty. We're saying we know exactly how our dynamics works. And if you looked at this with that update law, you would think that the covariance shouldn't change at all. In fact, you can see when we're away from the boundary, the covariance doesn't change. All of the points in this point mass just sort of shift together. And that's because our continuous dynamics are constant. So the Jacobian is just an identity matrix. You would think then if our reset map is an identity matrix, that it would have no effect on the covariance either. But you can clearly see here that the covariance, so the distribution on the right-hand side, is quite different than the distribution started out on the left-hand side. So something else is happening here. All right. And it turns out that the Jacobian of the reset map does not capture how the uncertainty changes when you go through a hybrid transition. All right. And so here, the reset map is identity. Nothing should happen when you go through that reset map. But you can see that the covariance does change when we do that. Covariance of this distribution. All right. And so how do we capture how the distribution actually changes? All right. And it turns out, I'm not going to go through the derivation, but the covariance changes using something called a saltation matrix. So if we have a variation, meaning if we are off of our nominal trajectory by some amount delta x, the variation after a reset map is equal to the saltation matrix times the variation before reset map, plus some higher order terms. Okay, what is the saltation matrix? The saltation matrix looks a lot like the Jacobian of the reset map. In fact, it's sort of mostly the Jacobian of the reset map. But then there's a bunch of other terms. And I'm not going to go into the details here, but these other terms capture the dynamics in the previous mode, the dynamics in the new mode, the guard set, the reset map, all of these other details from the hybrid system. All right. And so you can think of this as a correction term to the Jacobian of the reset map. And this captures that change that we saw in the animation there. So now if we go back to our Kalman filtering picture, on the left, when we don't have an impact, if we're moving along in a continuous flow, we're going to use the Jacobian of the flow. the Jacobian of our dynamics to propagate the covariance. And then, but then on the discrete part, when we have a discrete event, when we have an impact event, the covariance is propagated with the saltation matrix now, instead of the Jacobian of the reset map. And then this was all for the prediction step. There's sort of a similar story for the update step in the Kalman filter that's pretty similar here. So what does this look like? So if we use the saltation matrix to update the covariance, so here this is the start and end of that same system. So if you assumed that the Jacobian of the reset map was the update to the covariance, then nothing should change. So the red circle on the left should go to the red dashed circle on the right, which is pretty clearly not the covariance of the set of green dots here. But using the saltation matrix, we predict a covariance that's this yellow dashed line, which lines up almost exactly with this black circle, which is the actual covariance of this set of particles here. All right, and so we can very accurately propagate the covariance through reset maps without having to generate 1,000 particles, push them through the reset map, and then take the covariance at the end of it. Okay, so here's a slightly more complicated system, not that much more complicated. So here's a bouncing ball, all right, and so this is still there. You're in the air, and then you hit with some elastic impact law, and here we haven't sort of added more states. We've just made the dynamics a little bit more complicated because that constant dynamics was pretty simple. And here you can see that actually our final probability distribution is no longer Gaussian, right? It's got this weird pointy things on the corners. And so propagating the full probability distribution through this reset map would result in a non-Gaussian distribution. And this is kind of similar to any time you have a nonlinear system. You would use an EKF, an extended Kalman filter. The true distribution will not remain Gaussian. But even in these cases, the saltation matrix does track the covariance. So we can still get the mean from the reset map and the covariance from the saltation matrix. It's not that the mean, it's just that the mean and the covariance don't describe the full probability distribution, but it is the mean and covariance of the distribution. All right, so this was sort of pushing probability distributions through hybrid systems. If we want to wrap that up in a Kalman filtering framework, so now taking in sensor updates, sensor measurement updates, adding in some process noise, and going along, we can get here some Kalman filtering updates results. So here at the beginning, this is for that simple two-mode system, and I'm showing here, this is the state tracking, and the bottom. You can ignore the top. Just look at the bottom. The absolute error. How well are we tracking our state? And you can see, and I'm plotting. All right. So red is if you use the Jacobian of the reset map. Blue is if you use the saltation matrix, and then black is I think a 1,000 particle filter, which takes almost 1,000 times longer to run, but is sort of the most accurate ground truth here. All right, and what you should take away from these graphs is that all of the systems work pretty much the same before impact, right? So nothing's, and that's because nothing's really changed until you have a reset map, right? That's the main difference here. After impact, using the saltation matrix does much better than the Jacobian of the reset map, right? Because we're able to more accurately track our true uncertainty, our true belief after that impact map. There's still, if you look very closely here, right around the time of impact, there's still a little bit of error. The saltation matrix is not quite as good as the particle filter. And that's because with the saltation matrix, you're assuming that the entire probability distribution jumps across to the new hybrid mode all at once. All right. And if we sort of, if I pause this here somewhere in the middle, there's a lot of times right around impact where really some of your probability should be in one mode and some should be in the other. But in a Kalman filtering framework, we have a single mean and covariance that's our belief. So we sort of can't capture the fact that maybe some of our belief is on one side and some is on the other. All right. But once the sort of the rest of the probability mass moves its way through the reset map, then the saltation matrix works as well as the particle filter. All right, this was a very simple system. What if we tried on a more complicated system? So here, this is an asymmetric slip hopper that's higher degrees of freedom, nonlinear. We added a change of basis at the reset map to go from XY to theta at the toe and theta at the hip. And now we're tracking across multiple transitions. So you can see the gray is the time that the hopper is on the ground. So we've got, what is it, 1, 2, 3, 4 touchdown and 4 liftoff events that we're tracking through. And what you should focus on is this plot in the middle, where you see that the blue, which is using the Saltation Matrix, does much better than the red, which is not. And it's interesting here to note that the rest of these plots, so this middle one is the Y, and it's the vertical height state. The other states track pretty much identically to just using the Jacobian and the reset map. And that comes down to the fact that the Saltation Matrix is actually only a rank 1 update to the Jacobian and the reset map, right? Remember that first term was Jacobian and the reset map. That's really most of the story. This update works, it corrects one direction. For this system, it happens to mostly line up with the Y direction. And so in this direction, we can be much more accurate, have much more accurate tracking than using the Jacobian and the reset map. And in the other directions, it hasn't changed anything at all. So the estimate is pretty much identical in these other directions. All right. So what are the takeaways from this second part on state estimation? So this thing called the Saltation Matrix, with that sort of ugly expression, it's really sort of magical. It allows us to propagate covariance through hybrid reset maps. And that's sort of the key to getting something like a Kalman filter working on hybrid systems. Like an extended Kalman filter, the hybrid system is still really a nonlinear system. And so we should expect that the true belief to become non-Gaussian. But like an EKF, we can approximate it with a Gaussian and get sort of similar performance. And so all those sort of trade-offs with an EKF that you would have, we would get here. All right, and one of the things we're working on now is trying to do a better job of when we're just close to an impact, where maybe some of our belief should be before an impact and some of it should be after, or maybe there's sort of multiple events around there. So how do we sort of maintain belief in multiple modes, still within this kind of filtering framework? Let's see, how am I doing on time? Oh, all right, pretty good. So to wrap things up, today I mostly talked about contact and how do we handle the fact that contact is an inherently discontinuous process when we'd like to use tools that were developed for smooth systems and that work pretty well on smooth systems. If I come back in a couple of years, maybe I'll tell you more about some of the uncertainty and robustness stuff that we're working on. In particular, today we covered sort of how do we plan a trajectory that has changing contact conditions, and then how do we track a trajectory? How do we track our state when we're executing a trajectory that has changing contact conditions? All right, and in both cases, it really came down to sort of accurately capturing the impact event and fitting that in with smooth tools when you're not having an impact. There's lots of other cool stuff going on in my lab that I wanted to talk about that didn't kind of fit. So we've got a new paper coming out soon in TRO on tails and aerodynamic tails that I showed you before. Here's the sort of animal side of this picture. This video is from our collaborator in South Africa, Amir Patel. But we've also done a bunch of stuff on high-level motion planning for legged robots, grippers that you can smack into the ground and they're totally fine with it, as well as sort of digging in sand. And certainly digging in sand is a very different sort of way to contact the world than everything I covered today, right? So with my last, I don't know, -2 minutes or something, I just wanted to say a little bit about diversity and thinking about how you as an individual researcher watching this, you should think about what actions can you take to try and improve representation in the robotics community. Because it's no secret that the robotics community does not look like the rest of the country. And so what can you do to help improve representation in our world? And so one thing is to join a networking or advocacy organization. And so I'll give a plug to the Black in Robotics organization that was started recently by a different GRASP alumni, Professor Monroe Kennedy, who's now a professor at Stanford. Started this really great organization that's trying to do has lots of different activities. There's a committee for allies as well as members of the Black community. And there's other organizations for women in robotics. There's Black in engineering and Black in computing more generally beyond robotics. The next thing you can do is read, cite, invite for talks, mentor, collaborate with a diverse set of researchers. So there's this Black in Robotics reading list. So maybe after this talk, don't go to my website and read my papers. Go to the Black in Robotics reading list site and find some interesting research there that might be relevant to what you're working on. And then lastly, take a look at some of these other resources. There's a IEEE Spectrum article. And then these action item lists, these come from Black in Engineering and blackincomputing.org. These are really great resources. And they've got a lot of really good ideas about what we can do as individuals, what we can do as a university, what we can do as a professional society, all sorts of things that we can do. And I think it's just really important for everyone to take some time and think about what am I doing, what actions am I taking? Because if we don't take concerted action, then the sort of representation is not gonna change on its own. All right, and so with that, I'm pretty sure I'm out of time, and thanks for listening.
Thank you very much, Aaron, for that amazing talk. And I think now we will turn it over to our panelists, Diego and Matt, PhD students here at GRASP, to run the Q&A. In the meantime, feel free to submit questions via the Q&A mechanism in the Zoom webinar, and otherwise I'll get out of the way and let Diego and Matt take over.
Thanks, Michael. Maybe we can start with a question from Shane in the audience. Aaron, did you notice differences in the performance on physical robots when moving from lower order implicit Euler integration to the higher order orthogonal method?
Yeah, so those particular trials we've not run on robots directly, but no, we haven't tried that, frankly. But we've certainly looked at it. Something just changed here. Yeah, we've certainly looked at it for other methods, and I think the sort of, I could go back to the animations, but the sort of low order tracking, we kind of measure how close we're doing, and we know that there's always going to be this sort of speed versus accuracy trade-off. If we needed more accuracy, we could spend more time always, but this lets us get a more accurate for less time. Yeah.
I have a related question to that.
Yeah.
So as you know, the number of transitions increases in the trajectory. Do you see the sort of the difference in efficiency sort of widening or shrinking between implicit Euler and the orthogonal method?
So I would say that the improvement doesn't come so much from the number of transitions, because we sort of allow at any step, at any point along the way, you could have a force from any contact, right? So you're allowed to change contacts every single step, and so it's kind of has to compute that every time anyway. The improvement really comes from from being able to sort of interpolate in between. I guess I've stopped sharing, but if you remember the sort of speed versus accuracy chart, there's a lot of points along the way with the number of finite elements. And so for the same number of finite elements, it would take longer to do this. You'd get a more accurate thing. So all right, so you could add more finite elements, and it's until you got the same equal time or the same equal accuracy, you have to sort of think about that trade-off one way or the other. And so it comes from the improvement comes from not from how we're handling impact. The improvement comes from how we're handling all the time that's not impact. Everything in between the impacts is tracking more accurately.
Yeah.
So piggybacking off of that, Aaron, also great talk. What complexity is added by kind of inserting these non-regular time steps or events into your optimization?
Yeah, one way to think about it is you could imagine having, it's like you had an extra time step in between your other time steps where you just did this for 0 time. So in that sense, you could think of it as increasing the number of states in between, because now we have our sort of, at every boundary between finite elements, we have the velocity at the end of the previous one and the velocity, the new velocity in the new mode that could be different now, right? So it adds more decision variables in that sense. But again, for a given amount of time or for a given desired accuracy, it sort of makes up for it.
And actually, to follow up on that, the question of decision variables there is do we now have a variable amount of decision variables? Do the number of decision variables change through the optimization, or are we assuming we know how many events are happening?
It's just the scales with the number of finite elements. And so just like before, you'd have to say, all right, I'm going to give you, 100 points to play with and on the trajectory.
And you're just going to move those points to match up with your event.
Yeah. So it's very important then to allow the optimization to choose, and this is some of what slows it down. Allow it to choose where to put those finite elements. So time is a decision variable for each of those, which doesn't have to be a decision variable, although it does help, even if you're not doing this, to allow it to move those times around.
Great. Well, I think maybe I'll move over to the Kalman filtering. Is it tractable to consider multiple impacts within a single time step, and even possibly simultaneous impacts that happen at the same moment?
Yeah. So we sort of mostly show it with isolated, and if you think of it in a sort of extended Kalman filter sense, you're integrating your dynamics to do the forward propagation. And what you can do is just anytime you reach a contact event, you have to apply the reset map to your mean, and then apply the saltation matrix to your covariance. And you can just, however many you have until you get the next, you just keep, you sort of will continuously do that until you get the next sensor reading. So you can stack them together. If you wanted to, sometimes it's nice to write out like what would be the full DT, and then you sort of end up with a sandwich if you have your sort of continuous update, your discrete update, and then the continuous update in the new mode. So you can sort of build up these sandwiches that way. If you wanted it to sort of look at, this is the full effect over that time step. But I think it's easier to just integrate until you reach an event, run the reset map and the saltation matrix, and then continue to integrate. And then whenever you get a sensor reading, process that sensor reading with the sensor update.
So for impacts that are like very close to being simultaneous, and where the ordering the impact significantly changes the outcome, do you think it's possible to, create some sort of reasonable method that can capture that uncertainty through the unimodal approximation of the dynamics?
Yeah. So so I have a student that's trying to make this more precise right now, but the short answer is in the common sort of perspective, it's actually, you have this probability distribution, but it's really local. You're really saying, yeah, this is my state, and then there's some uncertainty around it. And so we know for that mean, the mean hits one event, then the other, or maybe it hits both at the same time, but we know which reset map to apply to the mean. And then there's sort of an implicit assumption. Anytime you have a Kalman filter on a nonlinear system, you're sort of assuming that your nonlinearity or that your uncertainty is smaller than your nonlinearity, right? That you're sort of not getting all stretched out. And so that would be the same here, right? Just like with any EK assumption. But there are ways to handle this. So if you have multiple transitions, the multifaceted version of the Kalman filter or of the saltation matrix is the Boulogne derivative, and you can apply that, but then you get something that's piecewise Gaussian instead of Gaussian, and so then we're working to sort of piece that back together in the resulting mode.
Okay, I'll ask one final question. I'll let Diego get back at you. So So, thinking about like a robust trajectory optimization and the sort of interplay between and even if there are small perturbations, do you think that there's maybe some way to, interface some of the ideas here with the Kalman filtering for uncertainty in measurement over the course of the execution of the trajectory?
Yeah, so I think there is a tension between trajectory optimization and robustness in that you actually often get really fragile results, right? Because if you want the absolute best, so the example I usually use, I guess, all right, so this is like a table or something, and I want to move my robot arm from here to here. The shortest path goes right next to the edge of the table. So if you ask for the shortest path, it'll give you a trajectory that just clears the table. And so if you think about uncertainty, there's a 50-50 shot you're going to hit the table, right?
Mm-hmm.
That's pretty bad, actually, right? So you're sort of setting yourself up for failure there. All right. So then the flip side is you can make really conservative estimates and say, all right, I know this is my state, but I could be anywhere within a meter of here or something. And then you end up taking these huge long trajectories that you didn't need at all, right? And because you're sort of, or you could take the opinion like, oh, someone could come hit me with a hammer in any direction at any time. And if you really thought that you could have a huge disturbance in any direction at any time, you would walk really slowly and very carefully, right? If that was really what was sort of possible. So there's definitely, with any trajectory optimization, there's a robustness versus optimality trade-off. And I think that the discontinuous nature of contact makes it even worse because of this sort of unilateral constraint thing. All right, how do we get out of this? I think one thing is the sort of convergent planning philosophy is to find trajectories that naturally reduce the uncertainty. So the idea is come up with a trajectory. Yeah, there's some uncertainty, but I want to make sure that that's decreasing over time. And maybe that's decreasing from sensor measurements. But if it's not decreasing from sensor measurements, let me see if there's other regions of the domain I can go through that try and reduce that uncertainty. And then we can be pretty sure that we stay pretty close to the trajectory we came up with. And we don't need as large a margin, a safety margin on that.
Great, yeah, I think I definitely agree with that sentiment. And I think there's something really special about contact to make you like give you really strong effects for decreasing uncertainty. If your foot touches the ground, you can be really confident in that. You have a very high confidence, the height of your foot much higher than you could even in a smooth system, which is, I think, an interesting, maybe counterintuitive effect of how discontinuity is affecting certainty.
That's true, yeah. And that, I mean, in some ways, it's sort of the most nonlinear you can get. And so it can be sort of as bad because it's discontinuous. So it can be as bad as possible. But it also means that if you jumped over that discontinuity, that's a really strong signal, right? And right now, you'll note in the Saltation Kalman Filter stuff, we're sort of not taking advantage of that strong signal, but we could be.
Yeah, I think Diego has a related question, so I'll hand it over to him.
Well, I think he's actually already answered it, kind of, but I will kind of combine a few questions that I'm seeing in the chat about the guards. So the first one was with relation to using that information. So, we're looking at the particle filter travel through this contact. But if at some instant during that particle filter's transition, we knew that we had contact or we had some, and this is the related to the question in the chat about the detection error, but we know that detection is imminent or it's happening. Could we use that information to actually even further shrink our covariance around our state estimation? And how robust can this kind of can this be to the detection error for something like a contact?
So I mean, the way that I've shown it here, the sensor information is in state but not contact mode, and so it's assuming that whenever the mean reaches the guard, that's when you transition, right? And so certainly you would want them if you had a sensor that was a kind of sensor that was more accurate than that, right? If it was less accurate than that, then it's not worth it, right? So we need a pretty accurate contact sensor. in terms of time. But certainly that would, assuming you had a perfect one, it would mean that you would just use that at that time. You would apply the reset map and the covariance update instead of when the mean reached the boundary. I think the way to think about, can your sensor information give you context state? If you if you have an explicit mode sensor, that's great. But if you take that same sort of nice flowing picture and just assume that the reset map moves you 50 units up, now when you get a sensor reading, if it looks like 1 or 2, you assume that you haven't transitioned. If it looks like 51 or 52, you can pretty safely assume that you have transitioned. And so you can sort of, it doesn't have to be an explicit contact sensor in order for there to be really good information about what your contact mode is, if you've transitioned or not.
Well, and to follow up on that, not only are we talking about whether we've transitioned as kind of sensing whether we've transitioned, but if we sense that we've transitioned, can we say something about where in our uncertainty range, which of these particles are feasible based on this measurement? It's kind of, so can we really shrink down onto, like, instead of the 1,000 particles that we started with, onto like 100 particles near a transition point?
Yeah, so if you had a strong, basically a sensor that said, all right, I must be near the boundary at this time, right? Then it's as if you had like in that case, in the X direction, you had a position sensor in the X, right? You have a sensor in the direction of that guard, and it's however accurate, so there's some covariance around there. And so you could fuse that in just like you would any other measurement update. Yeah. I will say for most, I might even say for most contact sensors, either explicit contact sensors or these sort of implicit contact sensors, they almost always tell you that you have transitioned sometime in the past. Right. And so so that's useful. That's great. If it matters when you transitioned, depends on your sort of dynamics. If you need to know exactly when you transitioned, then these kind of exponential filters that are sort of only looking at the current time aren't going to capture that as well. So we have a separate project doing sort of moving horizon estimation, because really I think often we have a sensor that says, oh yeah, you definitely hit the ground about 10 milliseconds ago. And so how do you use that information? Right. So you need to have sort of a receding horizon estimate in order to take advantage of the, and I think that's much more common. I think you can get good contact sensors, they just all have a lag.
And then I wanted to this wasn't one of the questions that I had thought of or that came out of the chat, but it came out of the previous comments you were talking with Matt about the trajectory kind of reducing the uncertainty. Does that start to look kind of like an optimized template or some sort of dynamics that kind of brings you closer to a specific trajectory? Some sort of attracting manifold, or what do you, if it's not the sensors, which is the other way that you can reduce the uncertainty?
Yeah, the idea there is that it turns out that it's based on contraction analysis, and there the idea is if you have certain conditions on your dynamics, it's not that you can think of it as it going down to a distinguished, this is the thing that I'm attracting to, but it's actually that any state in that region attracts to every other state. And so actually any trajectory is, all of the trajectories are attracting to, you can pick any of them as the one that it's attracting to. So I don't know that it doesn't quite have the, it's similar certainly to the idea of having some lower dimensional attracting invariant submanifold. But it's actually that all states are sort of attracting to each other. And certainly in a planning framework, you would plan one nominal trajectory and then hope that everything else tracks down to that one. But that's what you're going for. Yeah.
Wonderful. Well, thank you so much, Aaron. Thank you, Diego, Matthew, Michael.
Thanks for having me. And as I remember, after GRASP, there's pizza. So do I go upstairs for the pizza?
Yeah, you gotta go upstairs for the pizza.
Okay. All right. Thank you.
At this point, I would like to thank everyone a lot for joining us all throughout the semester during our GRASP on Robotics series. And as always, stay tuned as to what's coming up for the spring 2021 semester by following us on social media and checking our website.